because unfortunately the enumeration
has already been improved.
What's that?
By V. Z
Well,
has been improved by V.
That's right. Z has been improved by V.
So the question mark is beyond the previous improvement.
Fine. I was going to keep it simple, but.
Oh, well, Z is okay.
There you go. So that's where we want to be, is above both of those. So, to explain these are called enumeration schemes. We're going to give up on rationality, and all we want is recurrences. And they're going to be complicated recurrences. But anything, sort of any kind of finite system of recurrences is going to be fine for us, because then we get our polynomial time out of it. Okay, so the main object are these things that I'm going to call z-sets. So again, we have some B that's in the background. That's what we're trying to avoid. We also have some permutation. We might as well restrict to things that avoid B already. And it's going to be linked K. And then we're going to have some gap vector, which is a vector of non-negative integers of length K plus 1. And we're going to break up all of the B-avoiding permutations into these sets. So, this Z set, Z pi G. It's going to be the set of permutations. Now, it's a little bit tricky to write down what it is, but I think this will suffice. You have G1 entries, and then you have the first entry in pi. Then you have G2, and then the second entry in pi. And this keeps going until you have the kth entry of pi. Gk plus 1. And I only want to look at the permutations that already avoid. So this thing, I called it the gap vector. And that's because it's telling us exactly what we have between the elements of pi.
And you allow those gaps to be, some of those gaps can be 0?
Yes.
Okay.
The gaps can be 0. So my n includes 0. Yeah. And so obviously every z set is only a finite set of permutations because I've specified the length. So you know exactly what length all these things are. It's the entries in pi plus G1 plus G2 and so on. So let me give an example. If we had Z132, and then the vector 1, 0, let's do 2, 1, 0, 3. Okay, well, we'd have 2 entries before the 1, then the 1. Then 1 entry, then the 3, then nothing, and then the 2, and then 3 more entries. And of course, we want these to avoid whatever we happen to be avoiding. So that's this Z set. And the idea that Zeilberger had was that we always have some embeddings. We always have this embedding Z. The Z set for pi with a gap vector embeds. Well, what I'm going to do is I'm just going to remove one of the entries of pi. It embeds into pi minus pi of I. And if you think back to this example, when I remove one of these entries of pi, I condense two of the gap vector components. I'll call that just di of g, where di of g is g1 up to gi minus 1. It's gi and g plus 1 that get condensed, and then the rest is the same. So those two are the ones that get condensed. So we always have an embedding, and if this embedding is actually onto, then we have our recurrence. So our recurrence is when this is a bijection. Okay, so again, I mean, all these definitions are trying to capture the fact that some entry didn't play any part in whether or not we have a pattern. It's just what additional information they have around. Now, if you just try this, you're not going to have much success. Zeilberger had this big observation that, I mean, so we want this to work for all gap vectors. And he had this observation that it's not usually going to work for all gap vectors, but we don't even care if it works for all gap vectors. His observation was if this Z set is known to be empty, then we don't need a recurrence for it. And if it's known to be empty and we know how to recognize when it's empty, then we don't need recurrence. Okay, so I'm going to make another definition of reducible. So pi of I is, and this is actually this is my version of the Zeilberger enumeration schemes, so it's ES plus reducible. If I want this to be a bijection, so I'll take out pi of I, and I'll do what I need to do on the gap vector. But I only want this when this set is not empty. Okay. So, in order to implement this, what we do is we would just start going through the B-avoiding permutations and looking for these ES plus reducible elements. When we found one, we know we had a recurrence, so we could stop considering that branch of the tree. Okay. One interesting thing about this, as opposed to the other two methods, is that we don't know when this works. You just have to kind of run it. And at some point you might give up, or you might just keep going. But success is when we find that every sufficiently long permutation has an ES plus reducible entry.
But you have some examples where it's guaranteed not to work.
Yes, you can, by hand, you can prove sometimes that it's not going to work. I don't know how to do that by computer. So an example you might get of one of these schemes is, here's the empty permutation. Okay. It doesn't have any reducible entries, obviously. So we have to consider its children, which is just the permutation 1. The permutation 1 has two children. Oops. 1, 2, 2, 1. And then what we would see, and this is, sorry, I should write out what class this is. This is a real example. We're going to avoid 1, 3, 4, 2 and 1, 4, 3, 2. Okay, and we would see here that 1 is ES plus reducible. And over here, the 2 is ES plus reducible. but we need one condition on this. In order to make that reduction, we need that G is not greater than or equal to the vector 0, 2, 0. And if you think about that, if we have anything in the Z set, if we have at least 2 entries in here, then we either have R34 or R42. Okay, so these are the empty ones, and I'll indicate that with this. Okay. Over here, there are no empty Z sets, so I'll just not indicate it. So what we do is we say, okay, I mean, this is our recurrence, basically. We say everything has something and a 1 and something. We split those up depending on where the 2 is, to the right or to the left. Over here, we just say, oh, well, we can remove the 1. I've already counted those. Here, we say, well, if there's at least 2 entries between the 2 and the 1, we've got 0 of them. Otherwise, we get a recursion. So that gives us a polynomial time algorithm to compute these. So what I want to do is present the enumeration schemes and the insertion encoding in sort of the same perspective so that you can see how you can extend these. So perhaps we could call them insertion enumeration schemes. And to be honest, this is, I wanted to write a paper about this so I could spit it to your special issue, but I got stuck in the Maple code. So instead, I'll suggest this. This is a freebie problem for anyone who'd like to work on it. I think it should be done and it should lead to new enumerations. So let's come up with these IZ sets.
So it's not yet implemented?
No, this is not implemented. In fact, there are some theorems that need to be proved. So let's, looking at the Z sets, we took a permutation, now let's take a configuration. So remember, configuration has slots where everything's going to go, and if there's no slot, then we're not allowed to put anything there. So our gap vector is then going to be a vector of positive integers. And the length is the number of slots in C. And the IZ set, and when you're viewing it from this perspective, there's really no need to talk about the languages at all. In fact, the languages of the insertion encoding are kind of just because that's what Albert and Ruskuc think in.
So it's a red herring.
Yeah, in some sense it is a red herring. So the IC set of this configuration with this gap, this configuration with this gap vector is just the set of B avoiding filling, well, B avoiding, yeah, I'll just call them fillings of the configuration with GI elements in slot I. And so, for example, if we had slot 1, slot 3, 2 slot, and our vector was 2, 1, 3, well, we actually get exactly what we had over here. Right, we get 2 things, a 1, 1 thing, 3, 2, and then 3 more things. This is as before. Okay. Where the problem lies, in fact, there's sort of 2 problems, and the things I haven't really talked about. It's how the computer figures out if something is ES reducible. Okay. So figuring out if an entry is reducible for these schemes, if you use my approach, it seems to be just out of reach of what a computer can be expected to do. So I think what you have to do to be able to decide if things are insertion enumeration scheme reducible is to go back to an article in the Personal Journal where Zeilberger implemented these enumeration schemes with a much quicker way of testing for ES reducibility. So I think that's required in order to make this jump. Now let me show you one final thing. I'll show you an example of where this would help. So let's take our set to be avoiding 1, 2, 3, 4, and 4, 2, 3, 1. This can be done with the insertion encoding, cannot be done with enumeration schemes. And the way you can see that is
with a new extension, not with the old insertion.
yeah, it can't be done with the old one, with
So
WILF or WILF clause.
but can it be done with the ALR?
Yes,
It can be done.
so it can be done here,
But what about the question mark? Something can be
but not here. Yeah, it could be done in the question mark.
No,
I
but
wanna-
that exists something in question mark that cannot be done by neither of them?
Well, that's why you want to implement the question mark, is to figure that out.
Oh, no, right. Okay.
I don't know.
There was a question mark.
But if you look at Z sets,
Yeah.
like if my permutation is 5, 4, 3, 2, 1, I'm going to have problems whenever I have, let's say that they're all going to be 0, so I'll write the gaps here. But let me put a 1 there and a 1 there. Let's say that that's my Z set. Oops. Yeah, in fact, let's say that I'm looking at this underlying permutation, 5, 4, 3, 2, 1. And let's say I'm asking if a specific entry is reducible according to the enumeration schemes. The problem with enumeration schemes is I have to pick my entry before I'm given my gap vector. So it's like I pick the entry, the opponent picks the gap vector. If the opponent picks this gap vector, then all of a sudden removing this could be a problem because I could have these two entries could be playing the role of 4 and 3 in this 4, 2, 3, 1. Okay? But with the configurations approach, I know exactly what's in there. So if I'm given that configuration with the same thing, I would say, well, the one thing I don't want to try and remove is that. But I would actually see from the patterns that this 1 is never going to play any role because I know exactly where all the new entries are. And you might say, well, what if the opponent gave you, they said, well, the entries are going to be everywhere. And so if they restrict the slots, then I'll be able to rule one of the entries out. If they don't restrict the slots, then I'll go back to this, what I'm avoiding. I'll say, okay, because you don't avoid 1, 2, 3, because you avoid 1, 2, 3, 4, they're not all in increasing order, so you have a decrease somewhere between the slots. And now all of a sudden, you're going to have this, so I can actually rule out that configuration and never have to deal with it. So in that question mark, or indeed in the insertion encoding, this permutation, this underlying permutation will always have some sort of a removal. Okay, I'll stop there.
It will be there to answer questions in private. Thank you for a beautiful Blackboard talk. Good luck with the implementation. And let me know if you'd like to join us for dinner.